Okay, I think everything works fine now. We are live on YouTube now, and we are also recording this. So welcome everyone. Welcome back to our Warsaw University Observatory Tuesday seminar series. We are back after the break. We are now ready to begin the spring, summer semester with new energy and a new set of very exciting talks. The main theme for this semester will be related to planets. Not all the talks will be related to planets, but we begin with planets, and especially weird planets, with free-floating planets, with a talk from Dr. Przemek Mroz from California Institute of Technology. Przemek did his PhD here in the Warsaw Observatory 2 years ago, was it? Just 2 years ago, yeah, time flies. Yes, Przemek received multiple prizes for his PhD and during his studies as well. The IAU prize, the Polish Astronomical Society prize, and I probably don't remember many other prizes you received as well. Anyway, he's working on microlensing mostly in the OGLE project and also ZTF and other projects. And his field of expertise is the free-floating planets and seeing the unseeable. It's very hard to pronounce. So I stop here and let Przemek speak, please.
Thank you, Łukasz, for your introduction and the invitation to give this talk today. So a few weeks ago, when Łukasz asked me to present a talk on free-floating planets here at Warsaw University Observatory seminars, I thought, well, I already gave one at this seminar, but apparently that talk was nearly 4 years ago. And since that time, we had a lot of exciting new developments. So today, I'd like to tell you about our recent results on searching for and studying the population of free-floating planetary mass objects with the OGLE data. I will start my talk with a short overview of what is known about free-floating planets, both from the theoretical and observational points of views. Then I will talk about my results on measuring the frequency and properties of free-floating planets in the Milky Way. And in the last part of my talk, I would like to tell you something about the future of these fields, about future experiments designed to study the population of free-floating planets from using space-based microlensing experiments. So during my talk, when I'm talking about the planet, I mean an astronomical body that is less massive than 13 Jupiter masses, regardless of how and where it has formed. 13 Jupiter masses is, of course, the deuterium-Bernoulli limit, which is believed to be somewhere near the boundary between planets and brown dwarfs. By a free-floating, or speaking about free-floating or rock planets, I mean a planet that is not gravitationally bound to any host star. But before I will start talking about free-floating planets, I think I have to say a couple of words about gravitational microlensing. I am sure that most of people on this Zoom call know a lot about gravitational microlensing, but I suppose that there may be some students. So usually when we think about gravitational lensing, we are thinking about images of distant galaxies whose light is bent by the gravity of some intervening objects. Gravitational microlensing occurs within our galaxy. So microlensing occurs when the light from a distant star, known as a source, is bent and magnified in the gravitational field of an intervening lensing object. And so observer on Earth will see a temporary brightening of an otherwise constant star, and we call these brightenings gravitational microlensing events. And what is important is that microlensing does not depend on the brightness of the lens. So this method allows you to find objects that are dark, that do not emit any light, objects such as black holes or planets. So I have a short animation by Janek Skowron, which shows what happens during a gravitational microlensing event. So the light from a distant star is bent and deflected in the gravitational field of any intervening lensing object. Here it is a planet. So as you can see, usually two images, the shape of the source star is distorted. Usually two images of the source are created. In normal conditions, we cannot resolve those two images with the, at least with the current telescopes, but we can measure their combined brightness. And during gravitational microlensing events, the combined brightness of the source, the combined brightness of the images may be several hundred times brighter than the unlensed brightness of the source star. So every microlensing event has a characteristic angular scale, which we call an angular Einstein radius, which depends on the mass and distance to the lens. Basically, when the source star and the lens are perfectly aligned in the sky, the source star will appear as a small ring in the sky, and with radius equal to the angular Einstein radius. So in case of typical microlensing events in our Milky Way, Einstein radii are on the order of 1 milliarcsecond or smaller. And gravitational microlensing events occur when the angular distance between the lens and the source is usually smaller or on the order of 1 Einstein radius. So if you want to see a microlensing event, the lens and the source have to be closer than 1 milliarcsecond. So as you can imagine, the probability of such a chance alignment is very small. And this is why modern microlensing surveys are observing densest regions of the sky. They are observing the galactic center, galactic bulge, where the density of sources and lenses is the largest, and so probability of microlensing is highest. So typically, modern microlensing surveys are finding about 2,000 to 3,000 microlensing events every year. Unfortunately, usually we cannot measure the Einstein radius for the vast majority of microlensing events that we observe. And usually the only physical parameter that we can measure are Einstein timescales, or timescales of microlensing events, which also depend on the relative lens source proper motion. So if you have a lens and the source that are moving in the same direction, you will see on average longer timescale microlensing events. If the lens and the source are moving toward each other, then on average, you will see shorter timescale microlensing events. However, like integrating by all lenses and sources, like on average, timescales of microlensing events are proportional to the square root of the mass of the lens. So the lower the mass of the lens, the shorter the event. So typical microlensing events caused by stars have timescales of several days, like 20 to 30 days. Microlensing events by Jupiter mass objects have timescales of about 1 day, and microlensing events by Earth mass objects are extremely short. They have timescales of just a couple of hours. So if you find a large sample of microlensing events and you measure their timescales, you can try to get information about the mass function of lenses, including masses of those dark lenses, such as planets or black holes. And the first claims of a large population of free-floating planets were published nearly 10 years ago by Sumi and collaborators. What they did, they analyzed a sample of about 500 microlensing events detected by the Mroz survey, and they found an apparent excess of short timescale microlensing events with timescales about 1 day, NX is relative to what was expected from brown dwarfs and from main sequence stars. So they attributed that excess of short timescale microlensing events to a large population of Jupiter mass free-floating planets that should be nearly twice as common as main sequence stars in order to explain that excess. However, that work was met with great skepticism from the community, partly because it was very difficult to explain how such a large population of free-floating Jupiters could have formed. So basically, there are two possible formation channels. One possibility is that a free-floating planet formed in a way similar to that in which stars are formed. So by a direct collapse of clouds of molecular gas and dust. So it is believed that such star formation processes can lead to the formation of objects as low mass as a few Jupiter masses. And actually, we know a couple of such objects in our solar neighborhood. They are also called planetary mass brown dwarfs. However, we know that they are not very common. The frequency is much smaller than the frequency of stars. Another possibility is that a planet formed around a star in a protoplanetary disk, and it was subsequently ejected from its parent planetary system as a result of various processes. So the first channel is more likely to produce massive, giant, like Jupiter mass and super Jupiter mass planets, whereas the second channel, the latter channel, is more likely to produce a population of low mass, Earth mass, and sub-Earth mass free-floating planets. And as I said, there are many possible ways of ejecting the planet from its parent planetary system. Such possible processes include dynamical interactions between planets in multi-planet systems. We believe that such interactions may have been important during very early stages of planet formation, where you have many planetary embryos that are interacting with each other. They may be colliding, they may be falling, but they also may be ejected as a result of such interactions. You can have ejections from multiple star systems, ejections due to stellar flybys, due to interactions in stellar clusters. We know that the vast majority of stars are born in stellar clusters, so probably the environment may affect the planet formation and may lead to some ejections. And even free-floating planets can be formed at the very end stages of stellar system evolution, where you have when the host star enters the red giant branch, it can lose a significant amount of its mass in the form of stellar wind. So as the mass of the star gets smaller and smaller, its gravity becomes weaker and weaker, and in the end, the most distant planets can simply drift away into space. And actually, people think this is the fate of our Uranus and Neptune. So in several billion years from now, they may be liberated. They may drift away into the interstellar space. Simulations based on some population synthesis codes of planet formation predict that, for example, for a solar type-like star, theory predicts that typical masses of ejected planets should be around 1 Earth mass, and there could be up to like 20, 40 Earth masses of material ejected into space. So such low mass free-floating planets can be quite common. Other models based on models of late-stage planet formation around main sequence stars by Tom Barkley indicate that there could be like 2 to 3 terrestrial mass free-floating planets per every star in the Milky Way. And even our own solar system is not an exception with this regard. So some properties of the solar system, some properties of orbits of giant planets can be explained if we assume that solar system contained one additional ice giant planet that was ejected into space due to interactions with Jupiter. So we think that probably our own solar system may have been a source of at least one free-floating planet. So obviously, finding free-floating planets is extremely challenging, and because microlensing events due to free-floating planets are extremely short. So we in the OGLE project tried to measure the frequency of free-floating planets using the latest data from the OGLE project. As you probably know, OGLE is one of the largest and longest running sky variability surveys. The survey was founded by astronomers from University of Warsaw nearly 30 years ago. Since 2010, project is in its fourth phase, in which we are observing the densest regions of the sky, that is the galactic center, galactic bulge, the entire galactic plane that is visible from our site at Las Campanas Observatory, and also the Magellan Clouds. And we are interested in all kinds of sky variability, including, of course, gravitational microlensing events, all kinds of variable stars you can think of, and also all kinds of optical transients. In particular, some of our fields observed by OGLE, some of our fields toward the galactic center are observed at a very high cadence of either 20 or 60 minutes. So as you can imagine, such a very high cadence observations allow us to detect extremely short timescale microlensing events that may be due to planetary mass objects. And part of my work as part of my PhD was to analyze 50 million light years of 50 million stars observed in our high cadence fields with the main aim to search for those very short duration microlensing events. So because we observe those fields such frequently, we have like between 4,500 and 12,000 data points per every light curve. Our photometry is very accurate in these dense fields, 3% and 18 magnitude, 10% 19.5. So like in total, I was able to find nearly 5,000 microlensing events in those high cadence fields, of which about 2,600 passed our selection criteria for high quality microlensing events and were used to study the timescale distribution, which is shown here. So this plot shows the timescale distribution of our 2,600 high-quality microlensing events. This timescale is already, this distribution is already corrected for detection efficiency. And as you can see, like the vast majority of microlensing events that we observe have timescales between 1 and say 200, 300 days. The tails of our distribution have nice, like can be approximated as power laws with slopes of +3, -3. This is actually what you expect from theory. What we did not find was that excess of events with timescales of about 1 day. So to be more quantitative, we expected to find over 60 microlensing events with timescales shorter than 1.8 days. We found only 20, and this difference was even larger for events shorter than 1.3 days, where we expected to find over 40 events, but we found only 6. So obviously, it appears that free-floating Jupiters are not as common as previously claimed. So why is that? Why do we see such a difference? I think we still don't have a good explanation, but first of all, this may have been just a statistical fluke. So if you look at this difference, it appears to be large, but it's just 2.53 sigma difference, simply because the previous sample was very small. Another possible explanation are systematics in the data. So we think that some of those longer timescale events have their timescales incorrectly measured, which led to that apparent excess of events with timescales of about 1 day, which led to these claims of a large population of free-floating Jupiters. And very recently, I was talking with the first author of the previous work, and I know they are preparing a reanalysis of the data, and from what he said to me, apparently they also do not see in their new data set, they don't see this excess of events with timescales of about 1 day. So it appears that those free-floating Jupiters are not as common as previously claimed. So actually, we came up with an upper limit, with a 95% upper limit of 1 free-floating Jupiter per every 4 stars in the Milky Way. And these limits are more or less consistent with other constraints on the frequency of such objects in our galaxy. We also found we also found 6 extremely short timescale microlensing events with timescales shorter than half a day. As you probably remember from the beginning of my talk, such short timescale microlensing events should be caused by Earth and like super Earth, maybe Neptune mass objects. So here are the light curves of those 6 short timescale microlensing events. And as you can see, these light curves are not well covered with observations. We don't have, simply because those events were so short. And actually, we weren't fully sure whether these are real microlensing events or not. But on the other hand, we have been observing those objects for over 20 years, and we do not see any other traces of variability in our data. So basically, those light curves are flat, except for that one night when the object was magnified, which is why we think these are real microlensing events. And because our sensitivity to such short timescale events is relatively small, these detections are consistent with such low mass lenses being more common than stars in the Milky Way. So these results were published almost 4 years ago in Nature, but we did not stop at that point, and we wanted to learn something more about the population of these objects. In particular, it would be great to measure their masses. So as I mentioned at the beginning of my talk, we could only measure timescales of those short timescale events, and we know that timescales depend on the mass and distance and the proper motion. So it's very hard to disentangle physical parameters if you have only timescale of a microlensing event. So if you want to measure the mass of the lens in a microlensing event, you have to measure 2 additional quantities. You have to measure the Einstein radius. You have to measure theta r, which is angular Einstein radius. And that is possible thanks to finite source effects. And I will describe that in a moment. And you also have to measure the microlensing parallax. You have to measure the distance to the lens, which is much more challenging. This is practically impossible now, but maybe possible in the future with the next generation of microlensing experiments. So usually when we are thinking about microlensing in the Milky Way, we can treat the source star as a point. So typically, Einstein radii are much larger than the angular size of the source star, which basically means that the whole light from the source star is magnified during the gravitational microlensing event. However, as the mass of the lens gets smaller and smaller, its Einstein radius also becomes smaller and smaller, and at some point it becomes comparable to or even smaller than the size of the source star, in which case only a small fraction of the source is magnified, and you see that the light curve shape gets distorted. These are the finite source effects. So to illustrate this effect, let us consider a 2F mass lens located halfway between Earth and the galactic center. If the source star is a main sequence star with a radius of half solar radii or 1 solar radius, then you don't see any finite source effects, simply because the size of the source star is smaller than the size of the Einstein size of the Einstein ring. However, if a source is a giant, then finite source effects start to kick in because the size of the source becomes comparable to the size of the Einstein ring. So here's the light curve for a source with a radius of 5 solar radii, 10 solar radii, 15 solar radii. So you can see that the light curve shape becomes distorted, the magnification becomes suppressed, and by modeling the shape of the light curve, you can measure the Einstein radius, and so you have much better constraints on the mass of the lensing object. And this is why we decided to carry out special searches for very short timescale microlensing events with giant sources, because we hope to find some events exhibiting finite source effects. And these efforts proved to be very successful, as now we have several very strong free-floating planet candidates. So this microlensing event is our newest and I think most exciting discovery. This is OGLE 2016 bulge 1928. This is the shortest timescale microlensing event ever found with a timescale of just 41 minutes. So I really like this upper plot, which shows the 23-year-long light curve of that source star, which is basically flat, except for that one night, actually except for a few hours when the event was magnified. So this microlensing event shows very strong finite source effects from which you could estimate the Einstein radius of about 0.8 microarc seconds, from which we could estimate the mass of the lens to be about 0.3 Earth masses, which is 3 times the mass of Mars. So by far, this is the lowest mass object ever found using microlensing. Another example is OGLE 2012 bulge 1323. This event has a slightly longer timescale of 0.15 days and a slightly larger Einstein radius of about 2.4 microarc seconds, from which we estimate the mass of the lens to be something between 2 and 15 Earth masses. And we have several more candidates. All of those events show finite source effects. All of them have timescales between 0.2 and 0.4 days and have Einstein radii smaller than 10 microarc seconds. So actually with 6 events showing finite source effects, with 6 events for which we could measure Einstein radii, you can try to do some statistics. So for example, we showed that the frequency of those events, the event rate of microlensing events showing finite source effects, is basically consistent with our earlier estimates from our 2017 paper. So those detections are those detections confirm our earlier suspicions that such low mass lenses are very common in our galaxy. You can also study the distribution of Einstein timescales, which is shown here. So what we found was an apparent gap between planetary mass objects, all of which have Einstein timescales smaller than 10 microseconds, and Micronizing events due to stars and brown dwarfs, all of which have Einstein radii larger than 30 microseconds. So we see this apparent gap in Einstein radii, which we call the Einstein Desert. We also see a similar feature in the distribution of timescales, where we have several very short timescale microlensing events due to planets, all of them with timescales shorter than about half a day. And we have a second peak from stars and brown dwarfs. So if this gap, if this Einstein Desert is a real feature, it basically tells us that our short timescale microlensing events, those lenses must have formed in a different way than stars and brown dwarfs. So basically, we are still collecting data. We are still searching for those short timescale events to check whether this gap is real or not. But there is one caveat in everything that I'm telling you today. So the problem is that we are not fully sure whether our objects are free-floating or not. So the reason is that microlensing allows you to detect stellar hosts within about 10 astronomical units of the planet. So if there were a stellar host within 10 astronomical units, we would see its signature in the light curve of a microlensing event. Because we don't see any such signatures, we can only provide some limits on the star-planet separation, which are on the order of about 10 astronomical units. However, if the host star is more distant, it's like 20 astronomical units away or more, then we won't see its signature in the light curve of a microlensing event. To check for the host star. For example, we can use we can take high resolution images of our lensing system. So we know that the source and the lens are moving in the sky with a relative proper motion of about 5 milliarcseconds per year. So several years after the event, the source and the lens should separate in the sky. So if we take a high resolution image of our lensing system several years after the event, and if we detect any light at the position of the lens, well, this will tell us that the planet has a stellar companion. It's not free floating, it's just its host star is simply very far away. If we don't see any excess of light at the position of the lens, well, this will tell us that the planet is likely free floating. So these observations cannot be performed now with current telescopes, simply because the lens source separation is too small, and because the resolution of the largest telescopes, such as Keck and VLT, is not good enough to resolve these objects. However, we think that all of our free-floating planet candidates should be observable with the future telescopes, with the future 30-meter telescopes, such as ELT, GMT, that are currently being built. So we think that in 10, maybe in 20 years from now, we should be able to check whether our objects are indeed free floating, or simply they have a very distant stellar host. And even if they do, even if they are orbiting stars but on very wide orbits, these objects are no less interesting, simply because we are probing like a population of low mass, Earth mass, and sub-Earth mass objects that are at very wide orbital separations. This is a phase space that is currently empty, and probably such planets, such planets are inaccessible to any other detection method. So as I said earlier during my talk, so when we want to measure the mass of the lens in a microlensing event, we have to measure the Einstein radius. And that is possible for at least some of our events. But we also have to measure the parallax. We have to measure the distance to the lens. And such measurements are much more challenging, at least now with the current technology. So one possible ways of measuring microlensing parallaxes is to observe the same microlensing event from two widely separated observatories. And by widely separated, I mean that one observer is located on Earth and the other may be Spitzer Space Telescope, which is something like 1 astronomical unit away from Earth. So when you are looking at the same microlensing event from two different vantage points in space, you are looking at slightly different source lens configuration. So you will see that the times of maxima of the event observed from space and from the ground may be slightly different. And you also may see that the amplitudes are different. And by measuring this difference in the light curves, you can basically measure the microlensing parallax. You can measure the distance to the lens, and so you can measure the mass of the lens. And over the past several years, microlensing community has been using the Spitzer Space Telescope to measure microlensing parallaxes to a large sample of microlensing events toward the galactic center. I think that over 1,000 microlensing events have been observed, both from Spitzer and from the ground. And the main goal of that project was to measure the galactic distribution of planets. So we want to know whether there are more planets in the galactic center or in the galactic disk, how planet occurrence changes with the environment. But and I think in several years from now, we will conduct statistical analysis of those microlensing events observed by Spitzer, and we will be able to answer that question. Unfortunately, Spitzer could not measure microlensing parallaxes to free-floating planets. And the reason is that Spitzer's camera had a small field of view. So you had to select targets that were observed by Spitzer well in advance of observations. So basically, you had to send the list of targets to the spacecraft about a week before observations. So obviously that precluded any observations of microlensing events due to those very short microlensing events by free-floating planets. So we couldn't use Spitzer to measure their masses. So another possibility is to conduct a space-based microlensing survey. So instead of observing single microlensing events, you would like to observe millions of stars simultaneously from space and from the ground. And such an opportunity occurred several years ago with the reproposed Kepler mission, with the proposed K2 mission of the Kepler satellite, which observed several fields along the ecliptic. And one of the fields, called field 9, was toward the galactic center. So we thought this was a great opportunity to conduct this space-based microlensing survey with Kepler. So Kepler observed an area of about 4 square degrees for about 3 months, and observed all microlensing events or light curves, all objects that are within that field. But the problem is that Kepler was not designed to observed such dense stellar fields toward the galactic center. Like the Kepler pixel size was quite large, so within 1 pixel you had a lot of stars, and actually it was very difficult to extract any photometry from the data set. But fortunately, I think a few years ago, our own Radek Poleski was able to extract some really nice light curves of Micronizing events from Kepler, and I know that they have just concluded an analysis of K2-CN data with the aim of searching those extremely short timescale events. I think I still cannot say much, but I think several like short timescale Micronizing events were expected in the data set, if some were correct. But I know that like analysis of the data set has been challenging, and it was very difficult to measure Einstein timescales of those short timescale events, simply because of the pixel size. And yeah, I think that maybe we'll hear something more about it from Radek in the future. And looking further into the future, the Micronizing community is awaiting the next generation observatories, next generation space-based observatories, in particular the Roman Space Telescope, formerly known as WFIRST. So that telescope was chosen as a top priority large space mission of the 2010 Decada survey. This mission is capable of conducting large-scale sky surveys in the infrared, so you can go much closer to the galactic center, much closer to the galactic plane, where the event rates are higher, and of course with photometry of space from space you can conduct like continuous observations of the galactic center. So we hope that Roman will be able to conduct such a Microlensing experiment from space. I think we'll hear about it more next week from Scott Gowdy, but I have just a couple of numbers. So because Roman will be observing galactic center from space with continuous 50-minute cadence, it will be sensitive to extremely low mass objects. It will be sensitive to Mars or even moon mass objects. And like in the end, it will provide us with this complete census of exoplanets. So here are some simulations from Samson Johnson at Ohio. So we expect that Roman telescope will, first of all, it will allow us to detect objects with masses as low mass as Moon, and it should detect several hundred those very short timescale Microlensing events. So obviously, with such a huge sample, we'll be able to carry out much more sophisticated statistical studies. And the other advantage of observing Microlensing events from Roman and from the ground is that you can measure Microlensing parallaxes. So we expect that simultaneous observations of Microlensing events from Roman and from the ground, or observations of the same Microlensing events using both Spitzer and Euclid space telescopes, will allow us to measure Microlensing parallaxes. And so, like in combination with the light curve, in combination with finite source effects, these observations should allow us to measure masses, not Einstein radii. So we hope that those future observatories will allow us to measure the mass function of those planetary mass objects. And in combination with the next generation of 40-meter telescopes, we will be able to distinguish between free-floating and wildly orbiting planets. So hopefully, in several years from now, we'll learn much more about the population of these objects. So basically, this is the end. I want you to remember 4 things from my talk. First of all, that by studying the population of free-floating planets in the Milky Way, we can learn how important are dynamical interactions in young planetary systems. Basically, we can learn how messy the planet formation is, how many objects are ejected during these very early stages of planet formation. I hope that I convinced you that we can detect such free-floating planetary mass objects with gravitational microlensing. Our current results indicate that there is less than one free-floating Jupiter per every 4 stars in the Milky Way. But on the other hand, we see a large population of lower mass, like Mars to Earth to super Earth mass, free-floating or wildly orbiting planets. And basically, that's all. Thank you.
Okay, thank you, Przemek. I'll do the clapping, although it's not the same as hearing it live. Thank you for this. Questions to Przemek, if you have any, then please raise your hand in Zoom nomenclature. So meaning there under participants, you can select raise hand, then I will see that you want to ask the question, and you will be able to ask. While people are thinking, I have a standard question, how Gaia can help in this field. Already now or in future?
That's a good question. So one of the possible ways of distinguishing between like free-floating and wide orbit planets is to use astrometric microlensing. So if there's a host star, we may be able to see its signature in the astrometry. So I didn't do calculations, but I think that at least for some of those events, if there is a host star, and we may see its signature in the Gaia astrometry. But yeah, I probably need to do some more calculations to quantify that.
But you mean the astrometric microlensing effect or the separation?
I mean astrometric microlensing effect.
Okay. Yeah, because the host star is actually much more massive than the planet.
So you can see its effect on the microlensing on the astrometric microlensing, like by even if you don't see it in the photometry.
Okay, good. Alex, you were first to ask a question.
All right. Very nice talk. Thank you, Przemek. So I was wondering, you mentioned several space observatories. What about JWST? Obviously, it will not be as good as Roman because of the small field of view, but sort of spacer and sort of spacer way of observing. And also, how about the angular resolution? Could you do you think you can resolve the Einstein ring with some of the objects of the JWST?
So I think that JWST may be helpful in detecting the host star, so distinguishing between free-floating and widely orbiting planets again. So we expect that the lens and the source, the lens and the source are moving in the sky, so they should be separated like several years after the event. So with additional observations, high resolution observations from JWST, we may be able to detect the host star if it's there. I think maybe not in the case of those candidates that we have now, because they're far too bright for JWST, but probably Roman is likely to detect hundreds of more candidates, so they can be vetted by JWST. Not sure.
Well, let's hope that JWST survive long enough.
Well, this is what I actually realized. That's I'm not sure whether JWST will be operational for that long, but yeah. So this is one possible ways of using these high resolution observations from the space to try to resolve the lens and the source star.
Well, ELT should be online fairly soon, so maybe you can check that.
Right.
Hopefully.
Okay, Radek, next question, please.
I would like to comment on your question, Łukasz. So when it comes to astrometric microlensing, I would say it's more likely that Roman itself would be able to detect the host than with the help of Gaia. So for events we see from the ground, Gaia may be useful, but from the events that Roman will see, they will be too faint, mostly for Gaia, and Roman astrometry actually will be really good in this small field of view relatively to the whole sky that Gaia is observing. So maybe some help from Gaia, but not much in the Roman era. Which
is yet to come, while Gaia is operational and doing well. That's a tiny difference. Okay, any further questions or comments? Radek is still raising his hand.
No.
Okay. Okay, if there are no more questions, so let's thank Przemek again for this nice talk and the opening of this semester session on planets with a big kick. So we stop here and we meet next week, but if people are willing to stay online a little bit longer for informal discussion across continents, then please do. And I'll stop the streaming now and thank everyone for joining.